Hello. I am going to go over some examples of centroid and distributed load problems. The first example that I have is asking us to find the total area of the shaded area. Find x and y coordinates of the centroid of the area. All right, and it gives us a equals 8 inches and b equals 3 inches. All right, x and y coordinates of centroid. I'm going to work on that one because that also includes the total area. So while finding x bar and y bar, then I can find total area as well. So let's write our equations first. Integral of x tilde dA over integral of dA. Then I have y bar, y tilde dA over integral of dA. All right, let's see. Stuff that I got to figure out to be able to solve these integral is x tilde is y tilde. So let's go one by one. X tilde, remember, it is the centroid of area element measured from what axis? If it's x tilde, it's measured from y axis. The other one that I gotta find is y tilde. So that one is centroid of area element measured from x axis. I have to find the d area, which is the differential amount of area or area of element. And one other thing that I gotta find is bounds of integral, which basically what it is minimum x, maximum x, minimum y, maximum y if I'm integrating with respect to x or y. All right, so area element, area element, area element. So I have to find an element here. Let me redraw my area here really quick. I have x, I have y. The area element that I'm going to take is going to be like this. It will have a differential amount of x as its length, and the length of it at any given time is going to be y because it is on axis y. And I have the y function. It's y equal kx2. So first of all, let's find that k. I'm sure we can do that because look, when x equals 0, y is 0. That doesn't help much. When x equal 8, then y equals 3. That would be helpful. So if I substitute the variable, I have 3 equals k, my x is 8 over 2, k is going to be 3 over 64. Okay, I have that. The other thing that I'll do is I'm going to find x tilde, centroid of area element measured from y axis. This is very thin, so at any given time this area is at x tilde, y tilde centroid of area element from x-axis. It's a rectangle. Halfway is basically y over 2 is the y tilde. All right, so those are those two. Last thing, let's see, d area, it's a rectangle, so it's going to be dx by y. That's my area. So that's all I want. That's all I need. So let's just start having the integral. I'm going to start here again. X bar, x tilde, dA over dA. X tilde, I found it to be x. dA, I found it to be y dx over y dx. Okay, I have a problem. My variable here is dx, so everything in the integral needs to be based on x as well. So I got to get rid of that y, and thanks that we have this y here based on x. 2 is going to be 3 over 64 x2. So I'm going to replace this into the integral. It's going to be x 3 over 64 x2 dx over 3 over 64 x2 dx. Last thing that's left is the bounds of integral. What is the minimum x and what is the maximum x? In other words, this element is going to be starting from here and kind of move all the way towards end. So x, my x is changing from 0 all the way to x equal 8. So 0 to 8, 0 to 8. And I think I'm done here. If you do the integral, you get 48 inch 3 over 8 squared inch. And what is this? This is total area. So I already found the total area, and the x bar is going to be 6 inches. I'm going to do the same thing for y bar. Y bar, y tilde, dA over dA. Y tilde, I found it to be half of y, and dA is y dx, y dx. This, I already found it, so I don't need to do the integration again. I'm just going to put 8. Y, so I'm going to have 1 over 2 y2 dx, 8 squared inch. And I have to replace my y2 like that. So I'm going to replace it. So I'm going to have half 3 over 64 squared x4 dx over 8 squared inch. Now the limits of y, or y1 to y2, the minimum is right here, 0. The maximum it could be is 3. So it is from 0 to 3. Wait, I made a mistake. My variable is dx. So bounds of integral should still be based on x. Sorry about that. They still go from 0 to 8. For 1 second I thought I have the y. So 0 to 8. Sorry about that. And I'm going to get 7.2 inch cubed over inch squared, which is going to be 0.9 inch. And that is my y bar. In other words, let's see. X bar, distance from y-axis, is going to be somewhere here. Okay, this distance needs to be 6 inches versus 0.9. 1, 2, 0.9 is going to be right there. 0.9. So that's X bar. This is Y bar. This is where they intersect. All right, let's look at another example. These are very common types of problems that we're going to often see, that you have two functions intersecting, and the area or centroid of the area that is trapped between them is desired. So here the shaded area is desired, which it is between two functions. I like to call one of them y2, one of them y1. Okay, so I have y2 equals a, h, and n are given. So y2 is going to be 6 minus 6 over 8 cubed x3. My y1 is going to be 6 minus 6 over h x. Okay. It's only asking for x bar. X bar is going to be x tilde dA integral of dA. X tilde is centroid of area element, which is measured to y-axis. Okay, so let's find that one first. To do that one first, I need a element of area. Let me redraw it here quick. Something like that. I'm going to take an element like this. Okay. So I have x, I have y. This element has differential width of dx. This point right here is on function 1, which is y1. This one is y2. This length right there is y2 minus y1. Okay. So my x tilde, which is centroid of dA to y-axis, is going to be right there, which at any given moment is at located at x. So this is x. My d area is going to be interesting. D area is dx y2 minus y1. And I have the function for both of those. So it's basically going to be dx y2 6 minus 6 over 8 cube x3 minus 6 plus 6 over 8 x. And this is my area. So my area is going to be, let me simplify it a little bit, 3 over 4 x minus 3 over 256 x3 dx. All right, I have x tilde, I have dA. I gotta find my minimum and maximum x, which are the bounds of integral. X moves from being 0 all the way to being 8. 0 to 8 inches or meters. And I think I'm all set to do the integral. X bar is going to be x and then dA, 3 over 4 x 256 x3 dx over 3 over 4 x minus 3 256 x3 dx. This is going to be the result of this. Should I do one more step for you guys? Let's do one more step. It's going to be 1 over 4 x3 6 over cube 4. This is how I did it. x5 over 3 over 8 x2 minus 6 4 x4, and that's going to be 0 to 8. That's going to be 0 to 8. The final result is going to be 4.27 meters, and that is x bar measured from y. So if A is 8 meters, this is a little bit over half. So a little bit over 4.27 meters. Okay. Let's look at another example. Find the x coordinates of centroid of the area if the 2 by 2 square is not removed. Okay, so part A is just the normal find this shaded area problem. Okay, let's only focus on part A. Part A. X bar is going to be x tilde dA over integral of dA. Three things I gotta find: x tilde, dA, and bounds of integral. Okay, let's see. X tilde, so I need an area element. First thing I need to do. I'm going to take an element like this. This is my area element, has the width of dx, because this is my x-axis. At any point in time, it has the length of y. So my area is going to be y dx. My x tilde, distance from centroid of this and y-axis, located right there, so that's x. And bounds of integral, this area moves from x of 0 all the way to this x that I do not have. How can I find that second x, or x2? It's simple. I gotta say y equals minus 1 6 plus 2x equal to 0, and I find the intersection with the x-axis. Obviously, I get one to be x equals 0. The other one is going to be x equal 12. So this point is 12 meters. All right. I think I have everything that I need to find x bar. X bar, x tilde, which is x, dA, which is y dx, y dx. All right. I got a problem. Remember, variable is x. Everything needs to be respect to x. So I have x. I need to replace y by this function. Minus 1 over 6 x2 plus 2x dx minus 1 over 6 x2 plus 2x dx, x going from 0 to 12, x going from 0 to 12. If you want to do the integral, you're going to get minus x4 over 24, 2 over 3, x3 going from 0 to 12, minus x3 over 18, plus x2, 0 to 12. You're going to get 288 meters cubed, 88 meters squared, which is going to be 6 meters. So this area without, or maybe I should say this area is going to be 48 square meters. That was part A. Part B, that says, hey, find the square, find the x coordinate when 2 by 2 square is removed. All right, so first of all, let's just try to guess it. Okay, when the square is not removed, the centroid is right in the middle. That's where I expect it to be. It was right here before. Now I have removed the square. So what do you think is going to change? Is the centroid going to be closer to x, or is going to be farther from x? Remember, centroid is center of area. And by removing that square from the right side, now I have less area here. And I have more area on this side. And that is going to shift my x bar a little bit towards y-axis. So it's going to be shifted a little bit this way to compensate for that less area. But I don't know how much, and that's what I'm going to calculate. To calculate that, I'm going to use the principle of composite areas. Remember, you can just add them together. So to construct that, I have an x. I am going to deduct this square from it, which is a 2 by 2, to get to this shape. Okay. So it's summation of, it's going to be x tilde area something like this, minus x tilde 1 area 2 area 2. Okay, this I already found based on the integral, 288 48. So I'm gonna use just that one, 288. Oh, sorry, this is like this, 288 over area 1, which was 48. For area 2, I need to find x tilde, which is the distance between centroid of this area and y-axis, which is, this is 1, this is 6, so that's 7. So it's going to be 7. And the area of it is 2 by 2. That makes sense because the units match. Divided or minus area, which is 4 meters. Sorry, this unit here was wrong. And this is how I'm going to get. So the result of this is going to be 260 meter cubed over 44 meters squared. So it's going to be 591 meters. So you can see, as I was expecting, removing the area caused the centroid to be shifted a little bit this way because I have less area on the other side. Now in this way I have same amount of area both sides of this line, and that's what it means, center of this area. Since we're in this topic, let's do another composite area. Find the centroid Y bar for the beam's cross-sectional area. Y bar is the distance to x-axis. There are different ways that I can divide this area. I don't need to do integration because I can divide it into simple area. Look, I can do this. I can do area like that and then 2 rectangle on the side, okay, for the area. So basically I can do this, xy plus xy. Okay, that's one way. The other way is, hey, look at this. I can start with a big rectangle and then deduct one rectangle from it and then deduct another one from it to get to that shape. Okay, any way that you find to divide this area, it's totally up to you. They are all correct. They should all yield the same result. The way I'm going to look at it, I'm looking to find less area that I need to deal with. Each of those result in 3. What I'm going to do is I'm going to do this. One area that I'm going to call it A1 plus A2. Okay, so this is the route I'm going to take. So let's see. I'm going to draw it here a little bit better. Okay. X. Let's just take the y-axis, be right there. Doesn't matter, because we're looking for y bar, the distance to x-axis. So how much this goes up. All right, let's call this area 1. Let's call this area 2. The equation that I have for y bar is summation of y tilde area, summation of area. So basically, because I have 2 areas, mean y tilde 1, area 1, plus y tilde 2, area 2, divided by area 1 plus area 2. Okay, area 1 is going to have y tilde 1, area 2 is going to have y tilde 2. So let's figure each of those. I'm going to write it here. Area 1 is going to be, this is 240 plus 240 plus 120. And here is 120. So 120, 600 is going to be 72,000 square millimeters. That's area 1. Y tilde centroid, distance between centroid of this area and axis x, this is y tilde 1, which is 240 plus half of that, 120. $300 millimeters. You get the idea. Area 2, I'm going to go a little bit faster. It's 120 multiplied by 240. 240, 120. And that is going to be 28,800 millimeters. Y tilde 2, centroid of this area, with x-axis, which is basically half of the 240, and that's going to be 120 mm. That's all I need. Let's put it back in this equation. Area 1, 72,000. Y tilde 1, 300 mm, plus y tilde 2, 120 mm, multiplied by area 2, 28,800, over summation of area, 72,000 plus 28,800. So this will result, as you can see, the unit on top is millimeter cube, on the bottom is millimeter squared. The result of this, if you do the math, you're going to get 249 millimeters. And basically this length is 240, so the centroid is going to be somewhere here, a little bit more than 240. 249 mm is going to be centroid. All right, I'd like to get some distributed load problems in here too. Find reaction at fixed support A. Okay, so this is like a rigid body problem with a distributed load on it. Okay, so I have to replace this load by a force of F1 and find its distance to point A or to Y, doesn't matter. And remember, F1 is area under loading, and X bar is centroid of area. Okay, so let's see. X bar, let's just start with X bar because X bar has area in it already. So X bar is going to be X tilde dA over integral of dA. X tilde, I keep repeating this so you can just remember it. Distance, centroid of element to Y axis, and dA is differential area of the element, and bounds of integral. Those are the three things we need to find. So let me redraw this load here in order to be able to get an element on it. I'm going to take an element right here with width of dx, length of y. So dA is going to be y dx. Let's get rid of that y and replace it. So this problem, get rid of that w, put y on it. Doesn't really matter. Or change that y to w. Means the same thing. So basically what I have is to replace y is 3 1 minus x2 over 25 dx. This is my dA. Since we're at it, let's find x tilde, the distance between centroid and y-axis, which is x. So now let's do the integration. X tilde, which is x, dA, which is 3 1 minus x2 over 25 dx over 3 1 minus x2 over 25 dx. Bounds of integral. it moves from 0 to 5 meters. 0 to 5, 0 to 5. All right, if I do the integral, what I get is going to be 3x minus x3 over 75 from 0 to 5. Top is going to be 3x2 over 2 minus x400, 0 over 5. Gonna go next page. So x bar is going to be 10 square meters, 7.5 meter cube. So remember, this was my area under loading. The result of this is going to be 875 meters from y-axis. So let's see what I have. So far, we replaced that loading with a force, which is 10. You know, now I'm just realizing the units that I used. I didn't put units anywhere, and that's a problem. I should have put units, because y dx has units of meters, y has units of kilonewton per meter. So what I want you to what I want to ask you is, okay, there we go. Got confused for a second to put proper units there. Kind of got lost in having area. So the area that we have here is going to be kilonewton meters. Looks weird because it looks like a unit of moment. And here we're going to have a kilonewton because it's y dx. Y is kilonewton per meter, dx is meter. When you multiply those, you get kilonewton. Because it's a force, has units of kilonewton. Okay. All right. Now we're okay. So what we've done is we replaced this force or this distributed load by a force of 10 kilonewton located at a distance of 1.875 to end of the beam or y-axis. All right, now we can go back to our draw free body diagram of a beam, put active forces on there, and reactive forces. It's a fixed support, doesn't move in x direction, doesn't move in y direction, and does not rotate. So it has three forces. All we have to do is write our three famous equations of equilibrium. We get ax equals 0. Then we can write summation of forces in y being 0. And that means ay is going to be 10 kilonewtons. Summation of moment about point A being 0. Let's see, I have moment A, I have a 10, 5 minus 1.875 meters equals 0. Moment is going to be minus 3125 kilonewton meters. I got a negative, means the way I drew it on the free body diagram should have been the other way. Okay, let's look at another one of distributed load. So I'm going to go a little bit faster here. Okay, it just says find magnitude and location of resultant force. So basically, get rid of this load and just give me one force. Okay. F that I gotta find, the resultant force, is area under loading. I'm going to be careful about my units this time. And location of it is going to be centroid of area. So let's see. I usually like to start with centroid because it has area in it already. Okay. Centroid, I have, instead of y, I have w. Centroid of area measured to w in this case. All right, let me draw x. This is w. I am going to draw an element like this at an arbitrary random location, dx, and any given amount of time it's going to be w. So d area is w dx. I have an equation for w, which is 4 x square root of x dx. That's my d area. This has units of pound per foot. This one has foot. So the result of this area is going to be pounds. X tilde is the location of the centroid of this element to w axis. So x tilde is going to be x. So let's put it in the integral. I'm going to have x and dA 4 plus 2 square root of x dx over 4 plus 2. I like to write this one like this, to dx. Bounds of integral. X moves from 0 all the way to 6. 0 to 6, 0 to 6. So let's see. The first integral is going to be 2x2 plus 4 over 5, x5 over 2. And the second one is 4x plus 4 over 3, x3 over 2, 0, 6, 0 to 6. You are going to get 43.6 pounds. Top, you're going to get 142.5 pound foot. So the centroid is going to be 327 foot. So we found the centroid, but we also found the area. That was part of it. So we have a load of 43. So basically this beam now is going to be like this. I have a force of 43.6 pounds. Location of it to point A or to axis W is 3.27 feet. As a practice, find support reactions at A and B as extra practice.